Good morning to everyone. Today, in this lecture, I will explain the superposition theorem. Before going to the superposition theorem, let us see what are the objectives that are going to be discussed in this lecture. You are going to see the superposition principle statement. Secondly, you are going to see the step-by-step instructions to be applied for solving a circuit to find out the response in an element by using the superposition theorem. This is a statement of the superposition theorem. In any linear bilateral network having more than one independent sources, the response in an element is equal to the algebraic sum of responses caused by the each independent source acting alone. It means the response may be voltage across the component or it may be current flowing through the component. This will be equal to the algebraic sum of voltage across the component due to each independent source acting upon it, or it may be a current flowing through a component is equal to the algebraic sum of current flowing through the component due to each independent source acting upon it. So this is the simple application of superposition principle, which is used to know the contribution of DC and AC independent sources in a circuit. For example, to determine the performance of an amplifier, we calculate the DC voltages and the currents to establish the bias point. The AC signal is usually what will be amplified here. A generic amplifier has a constant DC operating point, but the AC signal's amplitude and frequency will vary depending upon the application. This shows the best example for the importance of superposition theorem in electronic circuits. Secondly, these are the steps to be followed while finding out the response in an element by using the superposition theorem. First of all, you are going to turn off all independent sources except one, which you are going to make it active. This turning off process will be explained in the next slide in briefly. The second step is we have to redraw the circuit after making the one of the source active and the remaining sources inactive. The third step is solve for the voltage and current in the new circuit. Turn off the active independent source and turn on one of the other independent sources. Repeat step 2 and step 3. Continue until you have turned on each of the independent sources in the original circuit. To find the total voltage across each component and the total current flowing, add the contributions from each voltage and current found in the step 3. Next, this is a turning off the sources. The first step that we are going to do in this superposition theorem is the voltage source should be replaced with short circuit. By making this, you are going to make it the voltage across that branch is equal to 0, and the current source should be made inactive. You are going to open circuit it, so the current through that branch is going to become equal to 0. And one more important thing is, while selecting the direction of the current in the circuit, we have to consider the same direction of the current throughout the entire problem or calculation, such that once you select the direction for current to flow through a component and the direction of the polarity plus or minus for the voltage across a component, you must use the same direction when calculating these values in all the subsequent circuits. So now let us see the response in an element resistance R1 by using the superposition theorem. Here I have considered a simple circuit which consists of three independent sources. One is the voltage source and the remaining two are the current sources IS1, IS2. I have considered the current that in the loop 1 as I1, which is in clockwise direction, and the current in the loop 2 is taken in the anti-clockwise direction and indicated with I2, and the current in the loop 3 is indicated with I3 in the anti-clockwise direction. So to show the clockwise and anti-clockwise difference here, I have shown the clockwise direction with a thicker line in the and the anti-clockwise direction with the thin line. So in the first step, I am going to take the voltage source Vs as active, whereas the other two sources are made inactive. Since these are the current sources, I have made it that branch as open circuit. So these sources will become inactive as the value of the current in the open circuit is going to become equal to 0. So whenever these current sources are open circuited, the current through in this branch is going to become 0, and there is no use of this resistance R2 because it is unconnected with the rest of the circuit. So in the next step, I am going to redraw the circuit by removing the resistance R2. See here, I have removed the resistance R2 so that you are going to have the resistance R1 and R3 in series and a voltage source Vs, whereas the current sources are open circuited here. The redrawn circuit will be like this. The voltage source which is having the resistance R1 and R3 in series. So the total resistance is going to become R1 plus R3, where the resistance R2 is removed here. So R equivalent is equal to R1 plus R3, which is equal to 50 ohm plus 20 ohm, which is equal to 70 ohm. So we know the voltage source value and the current, sorry, through the loop, that is I1 is equal to I3. So I1 is equal to voltage across total voltage by R equivalent, nothing but 3 by 70, which is equal to 42.9 milliamps. Similarly, we can easily find out the voltage across the R1 by using the voltage division rule or using the Ohm's law, which is equal to I1 into R1. V1 is equal to 2.14 volts, and V3 is equal to I3 into R3, as I1 is equal to I3. So both you are going to get the same current here, 42.9 milliamps, which is multiplied with the 20 ohms. So finally you are going to get V3 is equal to 0.857 volts. So in the previous slide, we have seen the current across the resistance R1 is I1 is equal to 42.9 milliamps. Secondly, I am going to remove the current source across the loop 2 and 3 to make it inactive, and whereas the voltage source is short circuited to make it inactive, and I am going to take the current source IS1 into consideration. So here only one source is going to act, that is the current source. So if we redraw the circuit in the next step, you are going to get in this manner. So here you are going to have the R2 is in parallel with R1 and R3, and the polarity of the current in the both the loops should be taken as we have taken in the first step itself. There should not be any change in the current direction. If you see clearly, the current directions, the voltage polarities in both across R1 and R3 are opposite here, and the entering current at the through the resistor R2 is equal to the the current from this current source, but in opposite direction. Now if we calculate the current across each resistor, we have I2 is equal to minus is1, because the current is in opposite direction with the current source. The current direction in the loop is in opposite direction with the current source, which is equal to 1 ampere. Here negative indicates the opposite direction here. And V1 is equal to minus V3, since the polarities across the resistance R1 and R3 are opposite here. So V1 is equal to minus V3. And current I1 plus I2 is equal to I3. R equivalent is equal to the total equivalent resistance is equal to R2 in parallel with R1 and R3, which is equal to 44.3 ohms. And if we calculate the voltage across this resistance R2, which is V2 is equal to I2 into R2, where I2 is nothing but 1 ampere. So in the next step, V2 V2 is equal to 30 volts. That is 30 into 1, where we have taken the reverse direction of the current with respect to the current source here. So minus 30 volts. And if you see the polarities here, V2 plus V3 is equal to R equivalent into I2, which is equal to minus 44.3 volts. Since R equivalent is equal to the total resistance, nothing but R1 in parallel with R3, and which is the total combination of this R1 R3 is in series with R2. So which is equal to 44.3 ohms, and the current is nothing but the total current is nothing but I2 is equal to 1 ampere, but taken in the reverse direction with respect to the current source. So minus into, that is 44.3 ohms into 1 ampere, which is equal to 44.3 volts. And nextly, the current across the resistance R1 in this case, due to the current source IS1, is I1 is equal to V1 by R1. V1 is nothing but 14.3 ohms volts. So by R1, where the resistance R1 is equal to 50 ohms. So finally we are going to get the current through the resistance R1 due to the individual current source is 0.286 amps here. So in the next step, we will see the effect of current source I2 here. So for that, to know the effect of this current source I2, I have open circuited the current source I1, and then I have short circuited the voltage source Vs, so that these independent sources have become inactive here. So after doing this, let us see redraw this circuit so that we will see the resultant circuit here. So this is the resultant circuit, R1 in parallel with R3 and IS2 in series with R2 here. Since we can see here V1 is equal to minus V3, but I1 must equal to I3. The only valid solution is to get this condition is I1 and I3 should equal to 0 amps. We will see this one mathematically in the next slide. See here, I1 through the resistance I1 plus I2 at this junction, I1 plus I2, since both are entering at this node, is equal to I3 plus IS2. So I2, we know I2 is equal to IS2. So this current, nothing but in this loop, is equal to IS2, which is equal to 2 amps here. And then if you see if you find out the voltage across this R2, V2 is equal to I2 into R2. I2 is nothing but the current source value, 2 amps, and the resistance value is 30 ohms, which is equal to 2 into 30, 60 volts. And let us consider this loop here. If we apply the KVL, Kirchhoff's voltage law, so 0 is equal to V1 plus V3. So I1 plus into R1 plus I3 into R3. I1 R1 is equal to minus into I3 R3. I1 is equal to I3 is equal to 0. To satisfy this condition, the resistance cannot become 0 here. So the current should be equal to 0 here. If current is equal to 0, then the voltage across this resistance is also going to become 0 due to this current source IS2. Next, if you are going to apply each individual sources alone, you are going to get whenever the voltage source Vs is on, the current I1 is equal to 42.9 milliamps, and then the current I2 is 0, we have seen, and the current I3 is going to become 42.9 milliamps, and the voltage V1 is 2.14 volts, and V2 is 0 volts, V3 is equal to 0.857 volts.